Roboticists dream of unboxing a robot that works in one target domain, such as our home, and can learn new tasks with few demonstrations. Several approaches tackle this goal. One trains only on target domain data, but these policies need much more than a few demonstrations, which can be infeasible for the end user to collect. Another method is to collect even more data from many different real-world domains to generalize to the target domain, but this can be prohibitively expensive. Yet another approach uses a hyperrealistic digital twin of the target domain to leverage abundant sim data to complement scarce real-world demonstrations. However, it is extremely engineering intensive to do system identification to match a sim environment to the target domain, and real-world physics can be hard to faithfully simulate. Even after these efforts, a Sim2Real gap would still exist. Can we avoid system identification by using natural language to bridge a large visual Sim2Real gap? Language could help extract information from abundant sim data when learning from a few real-world demonstrations. We propose learning domain-invariant representations with language. So we have a sim and real image both from a pick-and-place task. If they have similar language descriptions, then the sim and real image embeddings should be pushed together in our learned representation space, enabling the policy head to predict similar actions for both images, such as opening the gripper to place the object. Conversely, an image pair with very different descriptions should map to far away regions of the representation space so that the policy head can predict very different actions for the two images. We adopt the pre-trained fine-tune approach by first training a vision backbone, then adding a policy head. First, we aim to learn a domain-invariant visual representation through image language pre-training. For each image language pair from both sim and real, we encode the images with the trained CNN and encode the language description through a frozen LLM. We propose two pre-training variants. A, regression-based. The CNN must predict the language description embeddings of an image observation. However, we thought that predicting the exact language embedding value might be too strong of an objective. Thus, we additionally explore a relaxed variant, distance-based. The proximity between a sim and real image embedding should represent the similarity of the corresponding language descriptions. Second, we use the pre-trained visual encoder as the backbone of our language condition policy. We cast Sim2Real as a multitask learning problem on many sim tasks and one real target task. We freeze all but the last CNN layer, add adapter modules to process the task instruction, add a policy head, and do BC. We do Sim2Real on 3 tasks of varying difficulty, time horizon, and domain gap, including one with a coarsely simulated wire. At 100 target demonstrations, these are the non-pre-trained baselines, which were trained from scratch during BC either with or without sim data. MMD, the strongest of the prior Sim2Real baselines we tried, achieves an average performance in line with the non-pre-trained baselines. In general, vision language pre-trained baselines perform slightly better than the non-pre-trained baselines. R3M in darker green performs well on pick and place, but not on tasks with deformable objects like wire wrapping. Our method outperforms all others, including R3M, which is notable because R3M was pre-trained on 3,500 hours of real-world videos, while our method was pre-trained on just 100 real-world trajectories. Our results on wire wrap demonstrate the ability of language to bridge wide Sim2Real gaps with deformable objects. We also ablate the number of target demonstrations. At 50 target demonstrations, our method still outperforms all baselines. Our regression variant in dark gold tends to do better than our distance variant in yellow, perhaps because language distance is too relaxed a form of supervision for learning a high-dimensional image space. The same trend holds at 25 target demonstrations. We examined some rollouts from policies with our method. In stacking, most failures involve not closing the gripper enough. On two-step pick and place, our method mostly succeeds, but failures often pop up on the second step after finishing the first step. Our method can also wrap wires, but failures include grasping imprecision and premature gripper opening. To conclude, language can bridge the Sim2Real gap with domain-invariant representations, allowing us to outperform all baselines with only 25 to 100 real-world demonstrations. Our paper also has sim-to-sim results where the same trend holds. Our method outperforms all baselines and tasks with deformable objects, opening the door for a language to leverage low-fidelity sim data for Sim2Real transfer. Thanks for watching.